Okay, so I wanted to talk about the chain rule, and right now we're just going to start by assuming that we know what the chain rule is and do some examples. I have recorded the chain rule here, and I think in many ways the notation becomes a little bit, I don't know, it's a bit much to get used to until you're actually used to it. So, I have a tendency to prefer the Leibniz notation for the chain rule, and so there are many ways of notating differentiation. And in our book, the most common ones are this prime notation and the Leibniz notation, which has this ddx thing. Now, a couple of things. For one thing, this prime notation has a tendency to get lost in the notation, like, you know, when you say, I don't know, x squared minus 3x prime, like, that sometimes when people are writing it like that, it just, you forget that to see it, you don't notice it, or like you accidentally interpret it as a 1 or some other mark. And so, but this ddx is prominent, you're not going to miss it. Also, another advantage of the Leibniz is that it indicates which variable you are differentiating with respect to, which is important if you have an expression that has multiple variables or even multiple letters where some of the letters are meant to represent constants. So, I do like this quite a lot. So let's actually see what it looks like to differentiate a function. So in this case, I have 1 over x squared minus, or t squared minus 5. I would say in this case, like in terms of the statement above of f of t is supposed to be some composite function, f of g of t. In this case, it looks like the inside function is g of t equals t squared minus 5, and the outside function would be f of u equals 1 over u. Okay. So in the definition of the chain rule, there is an indication that, like, you could use df dt is the same as df du. Hang on. df du times du dt. And there are people that go through this, and I think that that is a lot notation heavy. I'm wanting to recognize this. It's important to see what is the outside function and what is the inside function. The outside function here is the reciprocal function, 1 over something. So I'm going to rewrite this as f of t equals t squared minus 5 to the negative 1 power. Then we can use the exponent rule, or the power rule, sorry. The power rule for differentiation. And so here's what I like to do. I like to write and see, I went and used the prime notation. So the derivative of f with respect to t is going to be, I'm going to differentiate this something to the negative 1. So it's negative 1 times something to the negative 2 times the derivative of that something. And whenever I use the chain rule, I almost always first write something like this with the blanks there, and then I will fill in the blanks with what that inside function is. That is t squared minus 5 okay, so this clearly delineates what our process is and what we need to do. So in this case, we have, I can rewrite this as negative 1 over t squared minus 5 squared. And now I have to differentiate this t squared minus 5, and that is 2t. And now simplify this, and this is going to be negative 2t over t squared minus 5 squared. Okay? So, next I'm going to do both sine squared of x and sine of x squared. Differentiate both. And we see in both of these cases we have a sine function and we have a square function, and the difference is which one is the inside function and which one is the outside function. So here, this can be rewritten as sine of x all squared. So here, the squaring would be the outside function, and this one, the squaring is the inside function. So I'm going to start with the derivative with respect to x of sine x squared. Now that outside function is the squaring, and I know that to differentiate squaring, I go 2 times the input, but then I have to take the derivative of the input. And that input is sine x. And now we see, so this is 2 times sine x, and the derivative of sine x is cosine x. And over here, to differentiate sine of x squared, well, the outside function is sine x, and the inside function is squaring. So the outside function is sine x, so I'm going to do the derivative of sine is cosine of whatever that input is times the derivative of that input. That input is x squared. And so the next step, this is cosine of x squared times the derivative of x squared, which is 2x. Okay, so let's actually write conclusion statements. The derivative with respect to x of sine x squared equals 2x. Oops, 2, not x, sine x. Sine x cosine x, and the derivative with respect to x of sine of x squared equals 2x times cosine of x squared. It's often a good idea to write these like polynomials out in the front of the, or a monomial out in front of the trig function. Okay, let's do a couple more. So the derivative with respect to y of this function, now here the outside function is the square root, for which we would use the power rule. So I'm going to do the derivative with respect to y of 25 minus y squared to the 1/2. So, using the power rule, this is going to be 1/2 times stuff to the negative 1/2 times the derivative of that stuff, where that stuff is 25 minus, oops, I went into preparing to differentiate. 25 minus y squared so this is 1 over 2 times the square root of 25 minus y squared. That's what that is, simplified. And then this piece, the derivative of 25 minus y squared is negative 2y. So we have that the derivative with respect to y of square root of 25 minus y squared is negative 2y over 2, oops, let's actually simplify this. We can cancel those 2's. Is negative y, let's go back to using blue, negative y over square root of 25 minus y squared. By the way, pro tip, it's maybe a good idea to memorize, just for the sake of being a little bit more quick sometimes. That the derivative with respect to u of square root of u is 1 over 2 times the square root of u. So we saw that in this case here. So you're always going to get at the same thing if you convert square root of u to 1/2 power and then do the power rule. Okay. Let's do this one. We have f of x equals e to the sine squared of x. So here we actually have 3 different things going on. We have an exponential function, we have a sine function, and we have a squaring function. So there's 3 different functions compiled, and you only really need to think about the outside one at a time. So you don't need to worry about all 3 of them at the same time and figure out how they all fit together. Just focus on the outside one and use that notation, and then you will see all of the pieces come out. So the derivative with respect to x of e to the sine squared x. So that outside function is the exponential based e, which we know is its own derivative from section 3.1. So this is going to be e to the something, and then we have to take the derivative of that something. And that something is sine squared x. Okay, so this is now e to the sine squared x times, now taking the derivative of this is the same as, that means sine of x, and then you square it. So the outside function is the squaring function. The derivative of the squaring function is 2 times the input, and then we have to take the derivative of that input. And that input is sine of x. Okay, and now this is e to the sine squared x times 2 sine x, and the derivative of sine x is cosine x. Okay. All right. So Back in section 3.1, we actually saw that the derivative of exponential base e is itself. That really depended on the specific definition of that number e, and we left the derivative of the other base exponential functions for later. And so now we're going to do that, and we are going to use the chain rule. And the key to that is to notice that you can change the base of any exponential function to any base you want to have. In particular, you can change it to e. So remember that y equals y equals a to the x is equivalent to saying log base a of y equals x. So, why did I just got lost in the way I was going to do this. What to do? Okay, so okay, this is not the most efficient way of explaining this, but also any number b is the same as the e to the natural log of b. That's basically because the exponential base e and the natural log are inverses of each other, and so this is composing those inverses. So that means if you have y equals b to the x, that is y equals e to the ln of b to the x power, which is, so raising one power to the other multiplies those powers, so this is y equals e to the power of ln of b times x. So the natural log of b is just a number at this point. Okay, so that's a constant. So what we have is a composite function, exponential base e with a constant times x. So if you take this over here, the derivative with respect to x of b to the x, this is the derivative with respect to x of e to the ln of b times x. This is exponential base e is the outside function, so this is e to the something times the derivative of that something, where that something is ln of b, oops, ln of b times x. Now we have, this is e to the ln of b times x times the derivative of this is just a constant times x, so the derivative of it is that constant, times ln of b. And the next thing is to recognize that e to the ln of b of x times x, again, this is going backwards in this whole thing. This is the same as b to the x times ln of b. So this is an important piece. The derivative with respect to x of b to the x is b to the x times the natural log of b. So if we were to do, for example, should have put this in there, Okay. So, if I want to find the derivative of this function, so in this case b is 2, so the outer function is the exponential base 2. So the derivative with respect to t of 2 to the t squared minus t is, the outer function is exponential base 2, so it is 2 to the something times the natural log of 2. That's what the derivative is in terms of that exponential. But then we have to take the derivative of that something. And so, oops. And that something is t squared minus 2t. So, continuing, this derivative is 2 to the t squared minus t times ln of 2 times the derivative of that inside is 2t minus 1. And that would be how we calculate the derivative of that. Okay.